Okay, we're going to look at tree diagrams for a second time, but here in a situation where the two events are linked in some way, or the multiple events are linked in some way, are dependent upon each other. So what has happened before can change what happens now, and that changes slightly some of the maths and how it works here. So here we've got a simple situation where there's one bag with 8 balls in, 5 red and 3 white. 2 are going to be taken out. Now it does not say one is taken out and put back in and a second ball is removed, and it does not say one is taken back, recorded and put back in. So crucially here, when the second ball comes out, there are only 7 balls in the bag, which means all probabilities will have changed, and that makes what the calculation is slightly different. But the setup at the start is just the same. We've got our starting position, and there are only 2 possible worlds that can exist after that. We can draw a red ball first, or we can draw a white ball first. And we split that up into our tree just like before, and that's all fairly straightforward. Now here the chance of a red is the 5/8, and this must be 3/8. So that's exactly the same as before. That's just keeping track of these numbers and doing the splits. Now here there are 2 colours left in the bag, which means there are 2 outcomes, and again they are red and white, and these are also red and white. So to keep track of that, we again draw our tree just like before, and this is where it gets different. We need to think a bit clearly and a bit more carefully what's going on. In this situation here, we've already taken a red ball out, so there are only 7 balls left in each of these in this bag at the time. Now if a red ball's gone out, there aren't 5 red balls left anymore, there are only 4. But the number of whites hasn't changed, it's still 3. So these fractions here are different from these fractions, and that's what makes this more complicated, is that you can't just put the same fractions and repeat them like we did before. Down here, again, we've taken a ball out, so there are only 7 left. But it was a white that's removed, so there are still 5 reds in here, and there are no longer, rather, 3 whites in here, there are only 2 left. So these 4 fractions are all different now on this section here, and that is new. That's what makes this trickier. After that, we use it the same way as before. So we look at what we actually care about in the question, and it's that they're different colours. So we need this outcome and this outcome. So to get along this branch, it's going to be 5/8 multiplied by 3/7, and this branch is going to be 3/8 multiplied by 5/7. We can put those through our calculator or do it in our head, and this is 15/56, and this is also 15/56. The total probability of this all happening together is this added to this, so 15/56 added to 15/56 is 30/56, which I think simplifies to 15/28, and if you prefer decimals for some reason, we can whack that through our calculator. It's going to be a nasty recurring one, 0.56-ish. No, sorry, 0.54-ish, misread that. Okay. So the multiplying and adding is identical to the previous work you've seen. The thing that is new is that in this story, the second set of probabilities are different from the first set because things have changed. If what happens first changes what happens next, it means this is dependent upon that, or this is conditional upon that, and that means these need to change. So telling apart when to make these change, when to keep the same, is the hardest bit of this topic. It's not the multiplying, it's not the adding, because that's the same in all the situations and you've got calculators. It's knowing what these values need to be in this second decision. So that can make this tricky. But once you keep track of that, this is just like the previous work. So enjoy.